Okay, everybody, welcome to the next session of the Distinguished Lecture Series hosted by HEAT at Aalto University at this time. I'm Sami Kaski. I have a great pleasure of introducing Professor Tommi Jaakkola from MIT, who will be talking about a broad topic, very much looking forward to what he has to say. So those of us who are working on machine learning know Tommi very well for the contributions that he has made both on the theory and applications, maybe starting from variational approximations. That's the first thing I've heard you have done. Some molecular models recently, and extremely interesting applications in computational biology and many other fields. I was asking Tommi that he is still so much a Finn, even though he has been... So you did your master's thesis at TKK, Helsinki University of Technology, but after that you did the PhD at MIT and have stayed at US since then. But I was asking, is Tommi still so much of a Finn that he prefers shorter introductions than a list of all his achievements, and he didn't give a kind of credible answer yet, so that's why I tried to balance. Now I've given some of it, but now I would very much like to hear your talk, so thanks a lot for joining us.
No? No. I have to talk very softly, apparently. All right, so this talk is about artificial intelligence, more from an engineering perspective. That's sort of the perspective that most of the recent advances have come from, not from the old style of AI, but more from an engineering machine learning side. And the goal is to use AI as an engineering tool to help accelerate and transform other areas. And in our case, it's really chemistry for the purposes of this talk. There's actually quite a bit of echo that I hear from here. I'm not sure if it's affecting you guys, but before I get started, I would very much welcome questions as I go on. I was unsure about the level of the material, so I'm going to try to keep it at a very intuitive level. And please ask for technical details or any broader or more technical questions as I go on for clarification. All right, so as a community, we're sort of well aware of the recent advances in realizing what I call an intelligent behavior, the ability to make predictions, the ability to simulate how things work, or control how things unfold. This has been in, say, in image analysis, understanding what the image is about, self-driving vehicles, intelligent assistants, superhuman game playing, machine translation, image translation, and so on. The role of machine learning in this process, in facilitating this sort of a transformational change, is really to enable us to sort of hop over what we don't understand or we can't really compute. For example, the mechanism underlying the semantic mapping from a sentence in one language to a sentence in another is not really well understood, but you can learn to bypass that by having examples of pairs of sentences and in a flexible way learning the mapping between the two. Similarly, in the game of Go, say, the branching factor, how many available moves you have in any particular game position, is on the order of a few hundreds. So the number of possibilities escalate very quickly as you start trying to predict what will happen and try to optimize that. But you can learn to control those cases as well. Now, within machine learning, there's been quite a bit of talk about deep learning, and in particular, deep learning has enabled us to make these hops in a very flexible, forgiving way, sort of a bypass what we don't understand. And one way to think about it is that with deep learning, you can easily specify procedures that are parameterized, that take a complex object as an input, processes it, and makes a prediction or turns it into another complicated object. And then you can optimize this process with respect to the parameters involved. And perhaps it's surprising that you are able to do it, optimize it so well. There are many reasons for that. But one downside of that is that as these models get more and more complicated, it's very hard to understand what they do, why they do it, and kind of rationalize the predictions that they make. The hope for this talk is really kind of push this frontier further in chemistry, sort of raising your head to make predictions, and then on the other hand, trying to understand what these methods are doing and reformulate them in such a way that you can actually get something intelligible and understandable out of those predictions. Okay, so the talk really has two parts. One is in the context of chemistry, raising your head, developing new methods in sort of a arrogant way of using machine learning to try to solve problems that chemists used to solve in different ways previously. In particular, I will focus on molecular optimization or drug design and machine learning tools in that context. The other side is then trying to interpret what are these models actually doing. Can we understand them? Can we verify them? Can we rationalize their behavior and develop methods that actually can give us some sort of a window into how these things actually work? Okay. Now, I would argue, and I will sort of very briefly towards the end give a little bit more, unravel a little bit more what this means. I would say that these are actually very synergistic goals. On one hand, make predictions, on the other hand, interpret and constrain the models so that they are interpretable, that actually enables us to do very deep generalization into areas that are not really focused in where the training data is. Okay, but this sort of end of the story here is actually very much the activity that's ongoing. So I will be a little bit cagey about how to go from there forwards. Okay, so because these areas have not yet converged strongly, I will illustrate them in two different contexts. There are sort of more complex models in the context of chemistry, and then the interpretability in the context of largely natural language processing tasks. Okay? And then sort of towards the end, and through discussion, hopefully we can sort of unravel where things are going and the current activities. Okay. So, starting with part one, raising your head to make predictions in chemistry. So the backdrop here is our desire to really turn chemistry into a realm of data science. There's quite a bit of information available about reactions, tens of millions of reactions in databases that are not fully utilized as far as computational tools are concerned. There is even greater wealth of information in the literature, chemical literature, that also quantifies sort of the context in which those reactions occur. And ideally, we would also like to make use of the notebooks that are in pharma companies that also contain negative examples. All the rest are positive examples. When it goes to a database, it's a positive example. Reaction occurs in a certain condition. What you publish, it's a positive example. We don't really have any negative examples other than those in the notebooks. Okay, so the hope is really to take all this data, put it in the computational form, and that requires several different tasks. And the hope is then to accelerate, say, drug design, molecular optimization, optimization of reactions, and so on. And hopefully also discover some new chemistry, new chemical reactivity that perhaps has been overlooked before. Okay? We started working on this problem a few years ago, and at that time there weren't really many papers on this topic, the cross-section of machine learning and chemistry. Now the area is actually exploding practically, so there's a lot of interest in this area. Sound better? Yes. All right. So we're not so arrogant as to try to solve this only as machine learning people. We actually have a larger collaboration of computer scientists and chemists and chemical engineering faculty, as well as about 10 major pharmaceutical companies that are contributing to this larger effort. All right, so what are our goals? We try to dig deeper into the literature, so use natural language processing tools to lift the knowledge that's in the chemical literature into a computational form so that it can actually inform the algorithms. We are looking at molecular properties. Can you predict what properties a particular new drug, say, has? Can we optimize that molecule to have better properties, more desirable properties? Maintain potency while minimizing toxic effects that it might have. We are looking deeper into reactions, trying to understand what comes out of a reaction, what is the major product of a reaction, and optimize those reactions in terms of conditions that need to be there. And also then finally, how to synthesize things. It's called retrosynthetic optimization. You're given a target, this is a drug you wish to manufacture. Can you tell me the optimal route, a set of chemical reactions that take me to that drug with the highest yield and other desirable characteristics? Now it would take a while to discuss all that, so I'm going to focus only a couple of these topics and essentially describe the sort of machine learning challenges and ideas in this space. All right, so let's look at property prediction as a simple example. This is how it was done prior to sort of machine learning people really entering the area. You have a molecule and you turn that into something called a fingerprint. Fingerprint is just essentially, you can think of it as a sort of a binary indicators of the fragments that occur in the molecule. Okay? You decompose the molecule into fragments, you just specify which fragments occur, and once you have a fingerprint, then you can learn the mapping from the fingerprint to the characteristics using examples of a molecule and its properties as training examples. Okay? So what we are doing now is actually learning also a representation for each atom in the molecule as to its chemical environment that it happens to be in. Okay? And we are learning how to aggregate those vectors into this adjustable fingerprint or continuous representation or latent vector or continuous fingerprint, as well as learning how to map that to the properties. Okay? So the whole pipeline is now optimized, and you learn to focus the model on the relevant properties of the molecule as part of learning to predict its properties. Okay, so for example, something called graph convolutional model is a particular way to estimate these things. It operates in the following way. You take an atom and you look at other atoms that it is bonded to. And if you now assume that you know the vectors for your neighbors, then the question is, how do I communicate the chemical environment represented by the neighbors to my atom and get my vector? Okay? The problem is that I don't know what that communication should be. Okay, I don't know what the vectors are, and I don't know what the communication should be. Okay, but I can introduce parameters. I specify the functional form of that communication. I specify parameters that I will then later optimize. Okay, so I'm defining a procedure for computing these things that has parameters and then optimizing the whole procedure, all the parameters end to end in order to maximize the performance of predicting those properties. Okay? So this is really what I referred to earlier as deep learning, giving us a very flexible way of specifying procedures that take complex objects and map them to some properties, and then we can optimize that procedure. Okay. Now, we don't actually operate in terms of these sort of flat vectors. We look at the multi-resolution version of the molecule. You can think of molecule having substructures that are relevant. You now create something called the scaffold. That's those substructures and how they are loosely connected to each other, as well as then the finer version of atom linkages. Okay, so you get, for example, a two-part vector rather than a single vector here. And then you can optimize this to relate to properties. Okay. Now, what I really want to talk about here is molecular optimization. So if you can make this prediction for each molecule, you learn this mapping. So now you have essentially a fixed procedure that takes a molecule, yields the properties. Then you can start asking the question of, what if I modified the molecule a little bit? What properties would come out? Can I optimize the molecule so that it has most desirable properties? Okay? Now, this would be a hard combinatorial problem because the molecular space is actually quite unwieldy. So in a sort of a deep learning context, we try to bypass that combinatorial optimization problem and instead optimize the latent continuous vector that's already related to the properties. Okay? And then if I do that, somehow I have to go back, and once I get a new vector, I don't know the molecule that it corresponds to, but I predict that if it had this vector, it would have a better properties. Then I have to also reproduce that molecule somehow, and there are many technical challenges with that, and I will highlight some of those. Okay? So we turn a combinatorial problem into a continuous optimization problem. Okay, so here's the vector you have. It maps to some continuous into this space. So the square you see here is really that space of continuous vector representations of molecules. And each of those vector representations now has a predicted property value. Here just a single one, but typically you would have multiple criteria. So the color here represents the property value that you are interested in as a function of that latent vector. Okay? Since you learned this mapping, you can create this sort of a landscape of property values as a function of the molecular representation. Okay? So then we optimize this molecule by just doing sort of a gradient hubs on the landscape, going towards the highest hill, while remaining reasonably close to where we started with. Okay? And then the hypothesis here now is that that new point corresponds to a molecule implicitly that has these more desirable properties. Okay? Now, the question is, can I reproduce it from this point? I have now just implicit representation of the molecule. If I could somehow reconstruct it from this, then I could give you a molecule that has these better properties. Okay? This is actually somewhat challenging. So if you go back and look at what we did here in the property prediction, take a molecule, turn it into a vector, predict properties, and then drive the whole representational framework towards maximizing performance of the properties. Okay? Now, what happens then about the vector representation? It forgets all the structural features about the molecules, anything but those that are directly relevant for the properties. Okay? So if I followed the previous slide routine, I could not reconstruct the molecule from these representations. Okay? The information is no longer there. Okay? So I need to drive these representations in more interesting ways. What we actually do is not only predict the properties from that vector, but also predict the molecule itself. Okay? So you have a starting molecule, turn it into a vector, you predict the properties, and you also drive it to be able to reconstruct the molecule you started with, so that you maintain the correspondence between the latent vectors and the molecules. And then if you get a new point, you can actually use this to predict what that new molecule would be. Okay? All right, so actually this is, there's a great technical hurdle here in reconstructing, say, labeled graphs from vector representations, okay? Deep learning has been incredibly successful in what I would call an autoregressive context, which is predicting things in a sequence. If you take a sentence in natural language, you can look at the words you already have and predict the next. So any object that's linearizable in this sense, or can be sequentialized, is very easy to learn to predict using autoregressive deep learning approaches. Okay? But labeled graphs are not sequentializable. Okay? So what we do here actually reconstruct the molecule in two parts by leveraging the fact that trees are actually possible to sequentialize, okay? So we choose the vocabulary of these substructures from which we create the scaffold in such a way that it's always connected as a tree, okay? So when I have now a vector, I need to reproduce a tree-structured object from that represents the scaffold. It is the tree structure, sort of what the substructure is at its node and how it is loosely connected to other substructures. Okay, that I can do in a sort of a sequential way by unfolding a tree. Think of a branching process. Okay. All right, and once I have the scaffold, then I can assemble things together, the substructures, the finer connectivity, in order to actually realize the corresponding molecule. All right? All right, so this is now how we drive these representations, and I gave you at least loosely the mechanism by which we take the vector and turn it into an actual molecule. So now you have a starting precursor molecule. You continuously optimize it through that landscape, walking towards higher hill. Now you get a new vector, new continuous representation, and you need to realize the molecule that corresponds to that. Okay? And we do this in these two sort of multi-resolution way by reproducing the scaffold first and then finer connectivity. Okay. So there are now two questions that you might ask about this process, maybe more, and you can ask more. I will answer two. First one is what I reproduce, is it even chemically valid object? Okay, it's all learned. Okay, it could produce something that's not even chemically valid. Okay, turns out that unlike some of the competing methods, we can ensure that it's actually 100% chemically valid. And that's because when you construct the scaffold, you can actually check the rules of chemistry that they are, since you are doing it in a sequential way, that they are actually satisfied. Okay? So at least you're getting an object that looks like a molecule. But since everything is learned as well, and what we related to the properties is the continuous vector, not the structure that we reproduced, we still need to check that that structure actually has the properties that we predicted it to have. Okay? All right, and you can show that at least about a year ago, we managed to optimize these molecules better than competing approaches. Okay? So, how many of you are actually sort of a core machine learning people? Excellent. So I can ask the next question. There's a fundamental sort of flaw in this thinking. What is it? It's not an obvious one, otherwise we would never have pursued the previous approach. Nobody's willing to. I don't think you can be seen through the streaming, so you are relatively anonymous if you offer. I will get to the diversity later. You could imagine that it's a weakness of the approach that I've described. It's not really a flaw in some sense. The flaw here is the following, that the molecules come in great diversity, small molecules, large molecules, complicated molecules, simple molecules. Compressing all that into a single vector makes that now seemingly Euclidean space very odd, right? There's an inherent information theoretic mismatch in terms of the object that you arrive at and what you're starting with. Okay, so this has bound to create some odd behaviors later on, and in it, it does. Here's an example. If you take three molecules that are similar to each other, quite similar, small variations of each other, okay, you map them all into these latent vectors. Okay, that's the triangle here. And inside the triangle are all sort of interpolated versions of these 3 points now in the latent space. Okay? So presumably you would expect, if the space of these vectors is nicely behaving, that these points inside would also be similar to these endpoints. Okay? Not all of them are. Okay? In the middle of the darker regions here are molecules that from that latent representation reconstruct into something that's quite different from any of these endpoints. Okay? So the complexity of the mapping from the diverse set of molecules to a fixed length vector, and the same issue is in machine translation. Early attempts were with the fixed length vector, that's no longer true. The architectures don't map to a sort of a fixed length representation, but a variable size representation. Okay? So we need to change how we do things. So we scrap there's sort of having a molecule and a property and learn from that setting to recasting the problem as a machine translation. Okay? The problem of translating, taking a molecule and translating it as if you were translating a sentence to a better molecule, maybe a sentence in another language. Okay? So we can learn this type of machine translation method by just having access to pairs of molecules. Here's a molecule, here's a similar one with better properties, and have pairs of examples of those. We can learn it as we learn machine translation model. Okay, so this bypasses this problem of having to condense things into this into latent space with obscure or complicated geometry. Okay, so what we do is we take as training data a molecule and its beta version, and then there may be multiple ways to improve. Just as it's possible to paraphrase a sentence, it's possible to paraphrase a molecule, maintain the properties, but express them in different ways. Okay, so our training data is this diverse set of pairs, and then testing is given a new molecule you have not seen before, translate that into a beta version. Okay, so just very quickly, I will highlight how this process works, what the architecture is, but I will not spend a lot of time on that. So typical machine translation methods have two parts, encoder and decoder. Encoder turns it into some intermediate representation, and then the decoder translates it into a new representation. So what we do here is the same multi-resolution version, but we don't collapse those vectors. You now have a vector for the chemical context of each of the substructures. You have a chemical context for each of the atoms, and you maintain it as a set. Okay? Then you decode it into a better version, sequentially generate the scaffold at every step of the way, attending to the substructures that were present before, and now you maintained a representation for each of the substructures in the starting molecule. Okay? All right. So this is still not addressing the question of diversity. So what you can do here in these type of procedures to incorporate diversity by essentially just fold in randomness into these representations and force the procedure to learn to utilize that randomness in order to take a simple naive randomization here and turn it into a natural diverse generation of the outcome molecules. Okay, it's again that procedural optimization. This sort of defines an implicit distribution over the possible target molecules. Okay, so does this work at all? And I will just illustrate briefly. Yes, it does, and it works substantially better than the previous one. The comparison bars have also risen since this field is moving quite fast. Well, this is just an illustration of turning a starting molecule into a molecule that has more drug-like characteristics. There are several sort of properties that you think a successful drug would have, and you can now, just as an illustration, turn the molecule into one that has better properties. Okay? So this is just a success rate that the nearby molecule that you propose actually has those characteristics that you want. And then also there's a question of the diversity of the candidates that you generate as alternative paraphrases of the molecule that all have better properties. Okay. So this is an illustration of sort of the deep learning architectures and procedures that are used for de novo molecular design, sort of not really using much of the information from chemistry, just using the data, specifying the architectures, and learning them in that way. Let's very briefly look at the same type of approach in the context of forward synthesis, which is just taking a set of reactants and asking the question, what comes out of that? What is the major product of the reaction? Okay? And the standard sort of a previous way to do this is to specify a large number of something called transformation rules That's essentially a regular expression that looks at the molecule and sees if there's a particular pattern, then I know what will happen. And you can apply these transformation rules. Okay, we are going to try to do this in a de novo synthesis way. So we just present the method, the set of reactants, and we try to reproduce the molecular graph corresponding to the major product. Okay, and we do this in 2 steps. First, you identify something called the reaction core. That's just a set of atoms and bonds that are likely to change as in the course of the reaction. And then you can create sort of a combinatorially a set of alternatives and rank them. Okay. The only thing I would want to highlight here is that predicting the reaction core is not actually a simple prediction task, because there's a red dotted circled part there in one of the reactants, and that participates in the reaction only because of the presence of that other blue dotted circled borohydride. Okay, so there are lots of these distal effects in understanding what comes out of the reaction. So as a prediction task, it is not trivial. Okay, so now I could give you a quantitative illustration of what happens here. I can also give you a more interesting one, human comparison. So can we do better than human performance in terms of predicting outcomes of reactions? Okay, so we did that at MIT, asked graduate students and postdocs in chemistry and chemical engineering, as well as a distinguished faculty member to rank what comes out of a reaction. This is the human performance chart. The success rate of, say, 56% means that your top-ranked choice is the correct one that comes out of the reaction, and 56% of the time, this particular individual succeeded in making that prediction. All right, and here's our column. And where does it go? I will reveal that shortly. All right. Anybody want to venture a guess where our first realization of this method fell along the human comparison of well-informed individuals? What was the guess at the back? 75. You are too optimistic. Thank you for your confidence, but no. It was just slightly before the best individual. Okay, and this was the first generation realization of the system. The human number 9 is the distinguished faculty member in chemistry. But the performance gap, even sort of based on the first attempt, was quite minimal. Understanding chemical one way to understand the result is that chemical reactions are actually incredibly complex, and it is very hard to understand systematically what comes out of them. And these methods are starting to rival human performance. Okay? What they don't do, however, and this is a sort of a failure of pretty much all the methods that are out there, which is that they don't really easily extend to new chemical species. Okay? You get a training data that defines some chemical diversity and space that you're operating with. These methods quite strongly try to focus the predictions around that. And if you extrapolate too far, they are not so good at making the predictions. Okay? So this is one thing that we need to fix, and actually the interpretability, as translated into our context, can facilitate these type of deep generalization that we are actually interested in, because when you are dealing with sort of a drug design, you are always venturing into new space, and you want the methods to be able to predict well in that extrapolated context. All right. All right, so that's as far as part one of the talk. I will switch gears and illustrate a little bit what we've done in interpreting, verifying, rationalizing predictions. But now I'm forced to illustrate this in a different context because the two areas have not really merged yet. We are working on it, but it's not there yet. Okay? All right, so demand for interpretability, sort of already obvious. Anything that is decision critical in medicine, in investment, in tactical decisions, and so on. We would like some kind of verification that the method that we rely on for predictions is actually capturing the real phenomena in the correct way. Okay, so many of the advances until now have come from optimizing performance rather than having this ability to for methods to be verified. Okay, interpretability is actually a very challenging concept. I would say that the problem with it is that humans are involved. It's very difficult to define exactly what it means and how complex the interpretation can be. So there are many facets and types of interpretability, and I will just run through very quickly the types of things that we've worked on to illustrate the range of things that you can think of. At one extreme, you would really want the models to uncover the underlying causal mechanism that realizes what you're trying to predict. Okay? And we've done this work in the context of game theoretic models that give you a causal understanding of decision problems. And you can learn those games from data. So uncover the causal aspects. You can force the method to highlight informationally what it pays attention to and what it does not. Sort of make it reveal its own decision process in terms of the information that it is using. Okay? You can look at mapping, say, a complex predictor. You can start from a very simple, like a linear model, totally insufficient in terms of modern complex problems, but it is very interpretable. And you can turn it into a more complex method while maintaining the simple interpretation. Okay? And finally, you can take a black box method that's already trained, somebody just gives that to you, and start probing sort of how does it actually work? What depends on what in that process? So the arc here is really from the underlying phenomena that you're trying to capture to focusing on the models that are already trained. Okay, and I will just very quickly take a couple of examples going backwards in this arc. Okay. So let's talk very briefly about how to understand, say, a machine translation method. Does it work? And can we understand what's inside the black box? So here's a black box. Somebody trained, say, we will be using Azure empty system because of the interface that was available. The sentence is translated via Google Translate, but it could be human, it could be any other black box. Okay? The question is, how do we start understanding this system? We can now perturb the sentence, the input sentence, and look what comes out as we pass that sentence, perturbed sentence through the black box. Okay? And then try to causally understand how the input tokens depend on the output tokens that come out. Okay? What are the dependencies really in this translation system? Okay? Sort of a glorified, randomized experiment design. Okay? It's a little bit harder because you cannot just randomize a sentence, you need to semantically randomize it. Maintain sort of a close semantic content and paraphrasing it and seeing what comes up. But randomized regardless. Okay? The understanding that comes out of that is necessarily local. It's around that sentence. Okay? I cannot give you a simple explanation for a very complex method. Okay? But locally, within a sentence, I can give you a simple understanding. But then globally, that method, that understanding changes depending on the sentence that you feed to the system. Okay? So even complex methods can be understood, but local. Okay? So here's just examples what comes out. The reddish colored balls here correspond to the input tokens. The blue ones are the translated ones. And I've illustrated sort of the token causal dependencies that you get here with the sort of strength of that gray line between the tokens. Okay? So what you can take off this slide is that actually Azure trained neural machine translation system and a human, they actually are quite different in terms of what is critical about the input tokens in terms of how it will be translated. Okay? You can analyze this a little bit further, understand the biases that are inherent in the system. So what we did here is to take an English sentence that's gender neutral. Okay? You don't need gender specification in the English version of the sentence that involves, say, occupation and characteristics and things like that. But when translated into Friends grammatically requires you to select gender. Okay? All right? So based on this analysis, we can see that the translation system is actually inherently biased. It translates words or puts a feminine designation for words like nurse, charming, and so on, dancer. Okay? And a masculine selects a preferably masculine form for doctor, professor, smart, talented, and so on. Now, this is clearly wrong, and it is not actually fault of the machine translation system. It is a fault of the data that was put in to train this method. Okay? You put in biased data, machine translation system will pick up on those correlations and then will function as a biased system as a result. Okay? So you can analyze these data biases in the system by using these token dependencies. Okay, last example here is if you actually train a poor dialogue system intentionally, and then just to illustrate that these token dependencies can reveal that it's not actually doing the right thing. So this was trained from a two-step movie dialogues. And the illustration here is for an input sentence at the bottom. What do you mean it doesn't matter? And the system responds, I don't know. Okay? How do you know whether the system understood anything about that sentence? Okay? Well, when you repeatedly feed into the system type versions, you see the dependencies that arise, and you can see that its answer only depends on the first two words of your question. Which means that the only thing it paid attention to, that it was a question, okay? It happily ignored the rest of the sentence. But you wouldn't know that by just looking at the answer. But by analyzing locally how these things behave, you can identify biases and weaknesses in these systems. Okay. All right, so based on the time, I'm going to hurry up a little bit. So another way to increase understandability is to not just look at systems that are already trained, but actually make them understandable by default. Okay? So here's a simple example. You have a linear model that tries to predict, say, the sentiment of a sentence or a document. you translate document into features, for example, what words occur in the document, and you have a linear coefficients there telling you how important each of those features were in terms of the decision. Very simple system, very understandable, but it's utterly insufficient for realistic tasks. So what you can do is turn this into a deep linear model where the coefficients themselves actually are input dependent. Okay? So architecturally, it still looks like a linear model, but there are much stronger dependencies incorporated into these deep linear coefficients. Okay? If you just train this model without any other changes, you would actually not get nice behavior. And I'm illustrating here in terms of images because it's easier visually to illustrate. Here, the bars are the features. I just have 6 features computed from the image. The bar is positive or negative value of the deep linear coefficient that the model predicts in response to that input image. Okay? The problem here is that when you give a slightly perturbed image, those coefficients are all over the place. Okay? So they don't actually suffice as a sort of an interpretation, even locally, for what the model is doing. So you need to work a little bit harder, and I will sort of bypass how to actually do it. You try to make these models to articulate these deep linear coefficients such that they are locally stable. Okay? So that locally, what they claim, what you compute as the deep linear coefficients are actually stable representations and highlight the locally linear version of the model. Okay? And just to illustrate that indeed that happens once you train it in the right way, you get locally robust linear coefficients that you can now interpret locally in the same way as you interpret a linear model. Okay? But globally, you get a different linear coefficients depending on the global region that you happen to be in. The method is complex, so you cannot get a linear model globally, only locally. Okay. All right, so I will skip perhaps the problem about inducing game theoretic models as causal mechanisms from data in the interest of time. But the idea is that you can actually learn models that are causal directly from data under certain circumstances. Okay. So, in the last few minutes that I have, let's talk just a little bit about how to bridge these two areas. Okay? We have complex predictors on one hand, and then illustrated methods in the context of natural language processing, how to try to understand these methods and to make them by default understandable. Okay? In the chemical context, and the same pattern is in other areas as well, in order to achieve this deep generalization that I mentioned earlier, you actually have to incorporate the domain knowledge in a much stronger way. So interpretability here comes from incorporating the physics into the models. Okay, so I mentioned molecular translation as a translation problem. I illustrated a method that tries to understand machine translation system in the natural language system context. You could in principle apply it in this context as well. But it is a little bit harder problem here because in the context of sentences, you know what the words are and you want an explanation in terms of words. That's not exactly true in the molecular context. You know some functional groups, but then there are others that you would potentially want to discover as explanations of how the system behaves. Okay? But it is doable, it's possible to proceed in that direction. Another way is to use physical calculations as features in the self-explaining architecture. Okay? So essentially, you're looking for a local physical model that explains around that example, around that molecule, how it behaves. It has the right invariance and sort of ability to generalize to a new context. Okay, and finally, I was going to talk about the causal, discovering causal models. The analog of that in this intersection of physics and machine learning is really to learn parameterized physical models. Okay? You specify a physical model at the right level of resolution. It has parameters that you don't know. But you can learn to predict those parameters and then take the output of that physical model as your prediction. You can combine physics and machine learning in many interesting ways. Okay? All right, so I guess, are there any funding organizations in the audience? I just wanted to make one comment here about sort of a success of this kind of work, taking AI into the realm of other areas. I would argue that that can be done only with teams of essentially 3. You need the foundation of machine learning for kind of rigor and generality that things are pushed to be more widely applicable. You need people who can think creatively about problem formulations and understand both sides, and you need deep knowledge of the domain that you're applying it to. You take any part out, and you're bound to run into problems. So this is what we are doing in this context, and this kind of setup is reproduced in medicine, material science, and other contexts as ongoing work as well. Okay. So just to wrap up, acknowledgements, we have the Consortium of Pharmaceutical Discovery as part of that. I have colleagues in computer science and chemical engineering and chemistry. And in particular, I highlighted work of one particular graduate student, Wenkong Jin. In terms of interpretability, the work that you heard was primarily from David Alvarez, that's a PhD student in my group. And with that, I'm happy to take questions.
Thank you, Tommi. Thank you for the nice presentation. Is this on already?
Hello?
Yeah, thanks for the presentation. So my comment earlier about diversity refers to the fact that when you're training any network or any machine learning system to provide solutions, if the solutions that you provide, especially let's say in the area of drug discoveries, if they're not diverse enough, when you try to map them to real life, real molecules, and they all degenerate to a single, just one or very, very few molecules, then you're not really exploiting very much. And the graph that you showed after that big flaw that you mentioned in the whole system shows that you're really localizing, and you're certainly not very much diversifying the solution. So if you can comment on that. And the other thing, if you can say anything about how you're doing this training thing with, I don't know, backpropagation or something else. Is it between the vectors, the feature vectors that you extract, or is it between the real or artificial molecules, if I may call them?
Okay, so in terms of the diversity, so the second architecture, the machine translation version, did explicitly incorporate randomization as a way of inducing diversity at the output. And you need to measure the diversity, and I give you one particular metric for that diversity. It's hard to characterize what it really is. Is it diverse in the chemical space? We have some metrics for that, but many drug companies that we work with are actually extremely interested in having methods that can venture into unknown chemical spaces. And to do that, you need to kind of characterize what the known thing is in order to be able to say that you are venturing into new areas. And we are working on these questions, but it's not resolved yet. The second question was about how to train these things. They get incredibly complicated. And this is actually a sort of a lucky coincidence with and perhaps the reason why deep learning architectures became so popular, which is overcapacity. So the models that you parameterize have a lot of, they have excess numbers of parameters that would be needed for that prediction task, okay? That excess volume, large volume in a high dimensional space actually gives a simple gradient method avenues to traverse through, okay? So overcapacity is actually helpful so long as you regularize and control the methods in various ways. So we essentially use the standard backpropagation for training these methods.
Thank you.
Very silent audience. Maybe I can ask if nobody. Oh, okay. Yeah, go.
Yes.
Go ahead.
I had just one question about the bias in the comparison. I mean, now you have focused on some data, and the data is biased in some sense in the translation dimension. So how can you show this both? I mean, especially for chemical. So if you just focus on some kind of chemical system, and then how can you produce a new one on this bias?
Right, so what you can do is once you identify the bias, say in the chemical context, you identify that it's doing something that's not chemistry, say. Now you can impose a regularizer that expresses that feature and specifically selects against it. So you can sequentially, essentially, you can think of it as adding constraints in the model. It wants to go and push in a different way that's non-chemical. You kind of cut that out. Maybe it pushes some different way, and you cut that out. And sequentially, you constrain it to have at least largely the right chemical characteristics. So that's one possible way to do it.
Are there any models that would explain the behavior of machine translation models on the semantic level? Whether those models capture semantics and how the semantics are actually represented in the models?
I can answer this very quickly. No. So that's a little jokingly, but it's close to the truth. There are certainly people who work on semantics and trying to sort of identify semantics from these models and incorporate sort of a semantic processing in the translation systems as well. So it's not unstudied, but in these type of architectures, it's very hard to we can't specify what semantics is. In some sense, in the translation systems, it is an invariance that you wish to maintain. You can detect when the invariance is broken, but it is harder to articulate what exactly it is. So these are essentially engineering tools. It's not sort of a developing theory of semantics. It's very much utility driven. If it seems to work, then you assume, just as say Google Translate is fully neural machine translation system, and you can tell that sometimes it really didn't understand the sentence. And you can try to correct those cases, sort of similarly to the answer to the previous question. You coax it to have the invariance that you believe is there.
So I've got two questions. One very quick, and the other the kind of the real question. So the quick one is that you showed the scaffolding structure for to sort of account for molecules that are not tree-like. But then the scaffolds that you showed were all tree-like. So is that actually a constraint, or was it just the way you chose the examples that it made look like that?
Sorry, if I may answer it quickly at this point before you ask the really hard one. The scaffold depends on the vocabulary that you choose as the substructures. And we chose large enough vocabulary of substructures and large enough substructures that any molecule in our training set you can put into a tree-like form as far as its corresponding scaffold is concerned. So we enforce it.
Okay. And then the next question was that, so I guess this is a hard question mostly for me because I can't formulate it clearly, so that's what I meant by hard question. Let me try. So the scaffold was meant for you to kind of decompose the complex structure into simple substructures. And then is the mapping that you learn from the substructures one to the other? Or so do you actually decompose the learning problem into improving one substructure at a time, or can the substructures somehow involve each other? And I'm thinking here about some non-local effects, so that if you kind of switch how this end of the molecule looks, it would kind of imply that you also need to make a corresponding change at another part of the molecule, so non-local dependencies. Or do you kind of only work with the local level, if you kind of see what I mean?
I understand the question, and the answer is we are incorporating non-local effects as well. So the tree-like structure that we unfold when you are translating it into a new molecule, you have a parcel tree, and you can fully auto-regress on the tree that you've generated so far in order to predict how things will unfold from there. So you have these non-local dependencies that are incorporated into the model and can be increasingly incorporated.
Okay, thanks very much.
Seems that this would be the time when we thank Tommi very warmly for the talk.